Yeah, my name is Connor Jordan. I'm a PhD student and research associate at the University of Edinburgh, and here on behalf of Thanasis and Chen. Thanasis has just had a baby, so parental responsibilities, and I'm here. But I do work on this project and on the model, so safe hands, hopefully. So I will go straight to our product, no slides. So this is the dashboard that our client would see. And so at the top left panel, we've got a short video just to demonstrate what we're talking about here, which is tidal stream energy turbines, and just demonstrating how they work and how energy is extracted or changed, transformed from kinetic energy to electrical energy. And the pilot product or project we use to demonstrate our pilot is the Maygen project, which is off the northeast coast of Scotland. And the reason we choose that product is because it has been generating, this project has been generating electricity to the UK grid for 7 years. And it's currently the largest commercial array of tidal turbines in the world. So on the top right panel, you can see the 4 turbines that they currently have installed. And if we scroll down, we'll get to the key piece of information that a tidal turbine array developer would want to be looking at. And that's these 4 colored lines, which shows over the past couple of days and the upcoming day, the energy that they expect to be able to extract using their tidal stream turbines. The black line then represents the current speed predicted by the model at the closest monitoring location they have for velocity. And so how are we doing this? What model are we using? But if I go over to our mesh tab, I can show you. We use the Thetis coastal ocean model. It's open source, and it's a depth average model, and it's got 2 key benefits. So we've been working in collaboration with Maygen, and there are 2 key things that are beneficial. First of all, if it will load, we have an unstructured mesh. There we go. So it's working at various different scales, which is important for this problem. So at the open ocean boundaries, we have resolution on the scale of kilometers. But if I zoom back in to where our turbines are, we have much finer resolution. So we're able to resolve the physics at a fine scale for our turbines, while simultaneously being able to understand what's going on in neighboring areas without having to have fine resolution everywhere in our model. And basically what this is doing is meaning we're simulating our hydrodynamics in a cost-effective manner. And the second thing that's important from an array developer, in their perspective, is that we simultaneously understand the hydrodynamics at the site, as well as determining the performance of the turbines, which is not always an easy thing to do. So sometimes you have a model that is separate from your determination of the performance of your turbines. And so it's not just a developer of these sites that might use it. We might have a tidal consultant or an energy consultant that wants to investigate new sites and help new clients or investors to understand the potential resource at other locations. So we focused in the inner sound here, but perhaps they want to look at the outer sound or further around the coast. All that we need to do to make this transferable to another site, another user, is change the mesh. And if we wanted to do this in the US or in Japan, we just need to change our input data as well as our mesh. But the exact same platform will work, and we can still get the same outputs. But it's not just the tidal array developers that are interested in this, because we've been in discussion with Maygen. It's also other parties such as the Crown Estate. So the Crown Estate are responsible for leasing out tidal energy sites, incrementing them in different stages. So if they want to understand all of their sites at once again, we can just change the mesh, but we're able to use the exact same platform. So it's very transferable. And so what will be important as we change for different uses and different users is to look at our outputs and compare them to the real data we have. So on the right panel here, we show the location of 6 gauges. And on the left, we show the key data outputs, so water level, flow speed, and flow direction. And so if we change the model, we'll be able to set up new gauge locations, input that on this platform, and be able to compare the modeled data with measured data. And so now is also a good opportunity to discuss who else we've worked with on this project. So again, Hydromod have provided us with this dashboard so that we can go from a Pythonic model to something that someone who doesn't have experience with code can easily set up and use and understand. Also, Romani are working with us. So when we download our data, the metadata is correctly set up, consistent with the ocean information model as well. And we've also had discussions with University College Cork to make sure that we're going along the right lines and consistent with what they perhaps do as well. But I'll head now back to the main dashboard and talk about two things I've not covered, which will be sensors and the future work. So in terms of sensors, MageGen themselves have provided some data for us. And the reason we've not used Iliad specific sensors is because the data that the MageGen project have provided us is already operating in incredibly harsh marine environments where flow speeds are exceeding 5 meters per second. And so it's already really pushing the limits of the sensors that the specialists have available to them. But what do we have left to do then? So at the moment, this is set up in an operational model or an operational demo perspective, and we can see what energy we've got coming up over the next few days and the past few days. But what we'd also like to be able to do is be able to predict for new stages of the project. So at the moment, they have these 4 turbines in, but what happens when they put in the next 20 turbines, which they have funding for, or they have allowance for another 100. So how do they go about that? So before the end of the project, what we will aim to do is add in our optimization features, which we already have the capacity to do, but just need to add to the dashboard so that a user is able to optimize the location of where these turbines go, which is fairly straightforward for 4 turbines, but how do you do that with hundreds? So the user will be able to do this from our platform. And on top of that, another key thing that we're currently working on and have a research journal paper, hopefully submitted by the end of the year, is looking at the impact of these turbines. So it's great to know how much energy we'll be able to extract, but what impact does that have on the environment? What about sediment transport, which we've just been talking about, for example? And so in order to do that, we have parallel model runs. We have one model with the turbines included and one without. And so we're working on that and the metrics needed to do this appropriately, and that should be done by the end of the Iliad project next year. The research paper that we're working on will also kind of work as user documentation as well. So short-term goal for the remainder of the Iliad project is this research paper, and the long-term goal will be implementing the optimization features. And I think that's it for me. Thank you.